In this video, let's see how to solve a harmonic analysis problem for a given axial bar. Okay, right. So the given question over here is that we have a bar, okay, as indicated in the diagram that we can see over here on the screen, where it is fixed on one end. Okay, it is actually a stepped bar for 0.5 meters. The cross-sectional area is 100 square, and for the next step, for another 0.5 meters, the cross-sectional area is 50 millimeters square. Okay, so one end of this stepped bar is fixed, and the other end onto the right side here, we can see a force is being applied in the x direction. Okay, right. So in a harmonic analysis, the force is going to be applied at a particular frequency, right? So for this, the given data is the Young's modulus, or the modulus of elasticity, is 2.068 into 10 power 11 Newton per meter square. Poisson's ratio for this particular material is 0.3. Density of the material given is 7,830 kg per meter cube. Okay, the load that is going to be applied, that is F of T, as indicated in the diagram, is a cyclic load for a magnitude of 100 newtons. Okay, the frequency range is 0 to 5,000 hertz. Okay, now let us see how to solve this problem. Okay, right. Okay, so this is the problem that has been given, right? So now we'll see how to solve this problem using the ANSYS software. So we'll go to ANSYS. Here we have the 15 version. Okay, so we'll click on ANSYS APDL. So the product will be launched. Okay, that is the software will open. Yes, now click on this window over here, click on run. Okay, and the software will be open. Maximize it to fit it to the screen. It's a structural problem, harmonic analysis. So first we'll go to preferences, we'll select structural and click on OK. Yes, next we'll go to preprocessor. Okay, we'll go to element type. Okay, we'll go to element type, add element, click on add in this window. Yes, in this new window that has come up, okay, it's a bar type of problem, so we can use link element. So we'll click on link and the element types. So here we'll select 3D finite 180 elements. So that is enough for this bar type of problem. And then we'll click on OK. So close this window. Yes, now we'll go to real constants, where we are going to input the cross-sectional area of the bar, stepped bar that is given. Right, so I click on add and add over here. So the element that is chosen comes into picture over here. Now we'll click on OK. And now the cross-sectional area. Okay, we have two cross-sectional areas. One is 100 square and the other one is 50 square. So first one will give cross-sectional area. Yes, so we can see here 100 square. Okay, so we'll give the cross-sectional area 100 100. Okay, we'll keep it in meters, so 0.0001. Okay, and then we have 50 square. Okay, so we have to give one more area, set number 2, real constant set number 2, and area will be 0.000, totally 4 zeros, 0.00005. Okay, that is in meters square. Okay, so we'll close this window. Yes, and then we'll go to material properties, material models. Okay, then here we'll go for structural, then linear, in that elastic, and then we'll select isotropic material, assuming that the material is isotropic. So here we are going to input the Young's modulus and the Poisson's ratio as per the given question. So Young's modulus is 2.068 10 to the power of 11. Poisson's ratio is 0.3. We'll click on OK and close this material model table. Before that, we'll give the density also. So just a second, I'll show this once again. So the below after this, once we give the Young's modulus and Poisson's ratio, once we close that window, in this material model, we have the density option over here. So click on that. Yes, in this window, we'll give the density is 7,830 meter cube, sorry, kg per meter cube. Right. So close this window. Now we'll go to modeling. We'll create the model. We'll go to create. Then we'll go to nodes. Okay, inactive CS. We'll click on inactive CS. First node is always at the 0, 0, 0, XYZ values, that is. Click on apply. Yes, second node. Okay, so one of the stepped bar, one step is at about a distance of 0.5 meters. So X value will be 0.5. Click on apply. Then the other end of the bar is at a distance of another 0.5. So measuring from the XYZ coordinates, it will be at a distance of 1 meter. So 0.5 meters plus 0.5 meters. Okay, right. It's nothing but 1 meter. Right. So here we have to go okay. So totally 3 nodes. So 1, 2, and 3. Okay, first step and second step of the bar. Okay, right. So we'll go to elements. We'll go to elements. Then element attributes. So here in this window, okay, the element type is only link 180, no change in that. Material number is, there's only one material, so no change. Real constant, nothing but the cross-sectional area which we had given, right? So real constant set number 1 defines the 100 mm square cross-sectional area, which should be between node number 1 and 2, right? So we'll click on OK. Now we'll go to auto numbered through nodes. We'll click on through nodes. So here we had the first step, okay, between 1 and 2. So we'll click on node number 1, click on node number 2, okay, and join them. Now we'll go to element attributes once again, okay, because the second half is another step having a different cross-sectional area. So material number will also not change, only the real constant set number defining the cross-sectional area is denoted by 2 over here. Okay, we'll select that and click on OK. Now we'll go to auto numbered through nodes. Click on through nodes. We'll click. Now we'll select node number 2 and node number 3. Okay, we'll select these two nodes and click on OK. So the other step of the bar is being created. Now so the model has been created. Now we have to apply the loads as per the given condition, right? So for this, we'll go to solution analysis type. Okay, it's a harmonic analysis that we are doing over here. So we'll go to new analysis. In this, we have to select harmonic analysis. Harmonic is the option that we have to choose, not static. Okay, so we'll select harmonic analysis, click on OK. Yes. Okay, now we'll go to analysis options. Okay, so we'll go for solution method, full solution method. And then once you click on OK, the next window appears automatically. In this, the equation solver is the program chosen, no need to change anything. Okay, and we'll click on OK. Yes, now we'll define the loads. Okay, load step options. Okay, and that will go to, in load step options, we'll go to time and frequency. Okay, yes. So here we have the frequency range has been given. Okay, so and the number of sub-steps we can decide. So frequency range, okay, number of sub-steps, we want 100 sub-steps. Okay, that is the intermediate ranges. Okay, and frequency range from 0 to 5,000. So 0 to 5,000 is the frequency range, and we'll go for stepped option over here. and click on OK. Now we'll go to define loads. We have not defined where is it, where the bar has been constrained, what is the amount of load applied. So we'll do that now. So go to define loads, click on apply, structural displacement on nodes. So we'll select node number 1 because it was fixed. Okay, right. So we'll select node number 1, click on OK, and in this window we'll select all degrees of freedom. Okay, because it was completely arrested. Right. Okay, then we'll go to force bar moment because 100 newtons of force was applied at node number 3, and that is the other end of the bar on nodes. Okay, we'll select node number 3. Yes, so load was applied in the x direction. So direction of force should be Fx. Okay, the value of the load is 100 newtons. Click on OK. So the load is also applied. So as per the given condition, the entire model has been created. I will go to solution, solve, current LS. Okay, click on OK. Yes, the solution has been done in the background. We'll close the window. We'll close this window also. Now let's see how the results are. So we'll go to, it's a harmonic analysis problem. So we'll go to time history post processor. Okay, go to time history post processor. Once we go here, this particular window will appear. Okay, and we'll select this add data, the first icon over here. First you have to add the data, right? So we'll click on this. So what do we need? We need the degrees of solution. So do of solution. Okay, in which direction? Here it is only in x direction. So we'll select only x component displacement. Click on OK. Yes. Okay, and we have to select which is the node. Okay, so we'll select the node number 3 over here and click on OK. Right. So we have the frequency automatically that has been given. It has taken up, and the node at which we want the displacement. Okay, now we'll go to graph data, the third icon over here in this window. We'll click on that. For this selected frequency and for the selected node, we will get the displacement in a graphical form. So here, if you look at this graph, the x-axis denotes the frequency from the range 0 to 5000. The y-axis actually indicates the amplitude or the displacements. So now we'll go to plot controls. Okay, then we'll go to graphs. Okay, modify the axis. We'll modify the axis. Okay, so that the labeling, everything is there as per our requirement. So x-axis label is the frequency. So we'll type frequency over here. And in the y-axis, we need the displacement. Okay, here it has been indicated as amplitude. It's nothing but the displacement. So we will label it as displacement only. Okay, and then only in the y-axis we'll keep the values in logarithmic term. Okay, and here we have the frequency range that we want. Okay. The frequency, the displacement in the y-axis, y minimum to y maximum. So we'll give 0 to 5000. Click on OK. Yes, now after we click on OK, we have this time history processor variable table window. We'll click on graph data once again. So the moment we click, this particular graph will change according to our data and the labelings that we have given. So here, once we click, the graph has been changed. The display of the graph has been changed. So here we have in the x-axis frequency ranging from 0 to 5000, and in the displacement we have it on the y-axis. So this graph we have to write it in the result sheet. Okay, after solving the problem. Okay, right. So this gives us the uh, harmonic analysis for the given type of bar problem. So here we can see a peak of displacement developed at about 1200 uh, approximately 1200 hertz, and then we can see another peak of the frequency at about 4000 200 to 4300. Sorry, the first peak is at about 1700. Then we have the next one at 2800, and then we have the other peak at the 4200 to 300 hertz. Right? Okay, right. So this is how we solve the harmonic analysis problem for the given bar problem. Yes. So yes, so this is how we can solve. Yes, yes, thank you.